Hello all the students. Today we are going to discuss two important things. One is the closure property and another is the partitions. So we will start with the closure properties. Now we have seen that a relation can be symmetric. In the previous video we did various types of relations. So in that we discussed what different types of relations can be there. And then we discussed the different types of relations such as the equivalence relations, the symmetric relations, the reflexive, transitive, all such kind of relations. Now we will discuss what is a closure property. So taking these types of relations, the concept of the types of relations, extending this thing and is what you know as the closure property. So let me start with, okay, any relation on a set. If there is a set A, there will be a certain relation on that set. Okay, so that relation may be on any basis. Like for example, I say set A is an element of 4 numbers and I want to find out a relation such that R is a set of coordinate pairs xy such that x is always greater than y. So whenever a relationship is formed on a set or on two sets, there is a certain criteria for that. Okay, so let us assume that our criteria for the formation of relation on set A is that set R, that is the relationship set. R here is representing the relationship set. So R is a set of coordinate pairs xy such that x is always greater than y. So of course, since R is a relation on set A, so all the x and y will be from set A itself. So how will the relationship set be formed? It will be formed on the basis that coordinate pairs xy such that x is always greater than y. So we can take 2 1, we can take 3 2, we can take 4 2, we can take 4 1, we can take 4 3. So we have to keep in mind that the relationship set will be formed using coordinate pairs in such a manner that the first element of the element of the coordinate pair will always be greater than the second element. The condition is x is greater than y. So there may be many such relationships formed on like this. So one relationship is formed like this on set A. There may be several other relationships that can be formed on A, like the other criteria can be x equals to y or x equals to 2y. There can be any criteria for the formation of relationship on a particular set. So depending upon the criteria, we can have a relationship set. There is one relationship which is satisfying this criteria. Then we can have another relationship set satisfying the criteria x equals to y. We can have another relationship set satisfying the criteria x equals to 2 twice of y. So basically what is this representing? The property of a relationship. That here what is the property? That the first element is always greater than y. So this is known as denoted by P of R. This P represents the property and this R represents the relation. So the property of the relation, like we discussed in the previous video, that various properties of the relations were, they could be equivalence relation, they could be compatible relation, they could be reflexive relations, they could be your symmetric relations and so on. So what are these? These are the properties of relations. Symmetric is one property of the relation, or reflexive is one property of the relation, or transitive, if it is transitive, it is one such property of the relation. So these are the properties of the relation, right? So on whatever criteria a relationship is formed, on whatever condition the relationship is formed, that criteria is known as the property of that particular relationship. So property is denoted by PR and this is known as the P closure. This PR means the property of a relationship set R, which is denoted by R. Now here I can also write S. There is no compulsion that a relation will always be denoted by R only. It is a convention that is being followed. So by default what we say, capital R represents a relationship set, but there is no compulsion. This can also be denoted by S. So in that case it will be PS. So by whatever name you are denoting the relation, so P or S or PR, it will be property of that. If the relation is represented using R, here you will write P of R. If the relation is represented using the symbol S, you will write P of S. So P clearly here denotes the property and S denotes the name of the relationship set. So this is known as the property of this relationship, and this property is known as the P closure. So this is what we were talking about, the closure property. So this is known as the closure property. Okay. Now let us see this with the help of an example. Okay, now if it is a reflexive property, if I say if it is the relationship is reflexive, so as per PR, right? Now R here is representing the relationship set, okay, and P here is representing the property of that relationship set, which we call the P closure, right? So if it is reflexive, if the relationship is reflexive is, so what is the property then in this case? The property is that it is reflexive. So P since represents the property, so instead of P we can write reflexive. And what is the name of the relationship? R. So we can write reflexive R. So we can call it the reflexive closure, right? So this is similarly, if the relationship is symmetric, if the relationship is symmetric, then in that case what is the property? The property of the relationship is that it is symmetric. So instead of P I will write symmetric. And if I am representing my relationship set with capital R, so I will write symmetric R. So hence this means what is it? It is a symmetric closure. Okay. And so like these two, if the relationship is transitive, that means what is this? This is the property of the relationship. This is the property of the relationship set, that it is transitive. Hence instead of P here we will write transitive. And if we are representing the relationship set through symbol R, then we will write transitive R. Hence I can say that this is the transitive closure, right? So this is the closure properties. Now how can I achieve a symmetric closure or a transitive closure or a reflexive closure? Now let us assume, this we will see through an example, that let us assume we have a set A having elements 1, 2, 3, 4 and 1, 2, 3 and 4. Now if I already have a relationship set, there is already a relationship set on set A having the coordinate pairs like 1, 1, 1, 3, 2, 4, 3, 1, then 3, 3 and 4, 3. Okay, so this is a relationship set A having elements 1, 2, 3, 4, and this is a relationship set on the set A having these coordinate pairs. Okay, now how will I achieve the reflexive closure? If I want the reflexive closure of this particular set R, how will I achieve this? Now please look here. As per the reflexive closure, both the first and second elements of the coordinate pair must be same. This is the property of a reflexive relationship. So 1, 1, I have it here. Then 3 3, I have it here. Now this implies for all the elements of set A. 1 1 is here, 3 3 is here, but 2 2 and 4 4 is not here. That means these two elements are missing. Okay, so as per the reflexive property, there are already two coordinate pairs having same elements 1 1 and 4 4, that I will not, and 3 3, that I will not consider. But 2 2 and 4 4, this pair is missing. So that means if I add to this, if to this set I add two more coordinate pairs, that is 2 2 and 4 4, will it not become reflexive? Yes, it will become reflexive. Now in the relationship set, if I have 1 1, 2 2, 3 3 and 4 4, this relationship set is reflexive. Then we will, apart from this, the extra coordinate pairs like 1 3 2 4, 3 1 4 3, which we are having, as I told you earlier also, that is not the concern. Even if they are present, that does not matter. What matters is that all these coordinate pairs with the similar elements in the first and second, as with the similar or same elements as the first element and as the second element of the coordinate pair must exist. So 1 1 2 2 3 3 4 4, if they are existing, and apart from that, even if some extra coordinate pairs are existing, that does not matter. Our concern is to see that all these elements are appearing in this format. So if 1 1 is there, 2 2 is there, 3 3 is there, 4 4 is there, I can clearly say that this relationship set on set A is reflexive. Yes. So what does that mean? To this already existing relationship set, if I add 2 comma 2 and 4 comma 4, I will achieve the reflexive closure of set R. Yes, if I add just these two coordinate pairs to this already existing relationship set, I will achieve, or I will get the reflexive closure of R. So that means I can say that the reflexive closure, reflexive R, is equal to R union 2 2 and 4 4. I can say that if I do the union of R with these two coordinate pairs, with this set having these two coordinate pairs 2 2 and 4 4, I will achieve the reflexive closure. Similarly, if I talk of the symmetric closure, if I talk of the symmetric closure of this relationship set, how will I achieve the symmetric closure? That is symmetric R. That means to already existing relationship set. If I do the union of this set with, now see what, in case of symmetric R, 1 3 is there, then 3 1s should also be there. This is here. If 2 4 is here, then 4 2 must also be here. It is not here. If 4 3 is here, 3 4 must also be here, which is not here. So what I need to do is that 1 3 and 3 1 are there. 2 4 is here. I will add 4 2. 4 3 is here. I will add 3 4. Now is anything else missing? 1 3 is there? Yes. Then 3 1 is here? Yes. Then 2 4, 4 2 is here. 4 3, 3 4 is here. So any coordinate pairs which exist, their opposites must also exist as per the symmetric property. So the opposite of 1 3, 3 1 is here. Opposite of 2 4, we add 4 2. Opposite of 4 3, we add 3 4. So now we have 1 3, 3 1, 2 4, 4 2, 4 3, 3 4. So that means if I have these two elements also in the relationship set, it can be called a symmetric relation. So therefore I can say that by adding these two coordinate pairs to this already existing relationship set, I can achieve the symmetric closure of the relationship set R. Hence I can say that R union coordinate pairs 4 2 and 3 4 give me the symmetric closure. So this is the definition of closure, that to an already existing relationship set, if I add the minimum number of required elements which help to achieve the closure property, then this is the closure, this is known as the closure property of a relationship R. Like here in symmetric case, to the already existing relationship R, I added these two minimum number of required elements or coordinate pairs to achieve the closure property, which is the symmetric closure. So hence it becomes the symmetric closure of the relationship set R. So this is the definition of closure property, that to an already existing relationship set you add the minimum number of required elements to achieve that property. That is known as the closure property of that relationship set. Now moving on, we will see partitions. Okay, so partition, if I have a set A having elements 1, 2, 3, 4, 5 and 6. Okay, so what is the definition of partition? This is a set A having elements 1, 2, 3, 4, 5, 6. So the definition of partition says that the grouping of a set into different subsets, non-empty subsets. You group them into non-empty subsets such that no element appears in more than one subset. So there is no repetition. There is no repetition of any element in any subset. So two things you have to keep in mind for a partition. It is very simple. Whenever you make the partition of a set, first of all you have to break it into subsets. How? In such a manner that no element is appearing more than once in any subset, plus all the elements are there in one of the subset. None of the element is missing. You cannot miss out any element while creating these subsets, first of all. So every element has to be there in either of the subset. Plus none of these elements can be repeated in any of the subsets. If one has appeared once in a subset, it will not appear in any other subset. Now let us look at the example. So as per the example, we can have a partition. There is a partition, for example, one partition can be 1, 2, 3, 4, then 5, 6. This can be one such partition. Another partition can be 1, 2, 3, 4, 5, 6. This can be another such partition. Third partition can be like 1, 2, then 3, 4, 5, 6, or we can have partitions like this: 1, 2, 3, then 4, 5, then 6. So in any manner you can have the partitions, but the only condition is that all the elements must be there in one subset and none of the elements must be repeated in any of the subsets. So like here, this is the one subset, this is the second subset. Then here this is the one subset, this is the second subset. This subset 1, subset 2. Then subset 1, subset 2, subset 3. So you can clearly see that in all the subsets, all the elements are included. This is subset 3. All the elements of this set are included in all the subsets, plus none of the element is repeated in any of the subsets. So this is subset 1, you have 1, 2, 3, 4. Subset 2, you have 5, 6. This is one partition. Then subset 1, you have 1, 2, 3. Subset 2, you have 4, 5, 6. This is another partition. Then subset 1, you have 1, 2. Subset 2, you have 3, 4, 5, 6. Another partition. Subset 1, you have 1, 2, 3. Subset 2, you have 4, 5. And subset 3, you have 6. Another partition. So you can partition a set into multiple ways, but the only thing that needs to be taken care of is that while dividing the set into subsets, all the elements of this set must be taken in one of the subset plus none of the element must be repeated in any of the subset. Only then can it be called a partition. If I take this partition, if 1, 2, 3 and 5, 6 is here, then this will not be called a partition of the set A because 4 is missing here. So 4 needs to be here. Also, if I have this subset, say for example 1, 2, 3, 4 and then another subset is 5, 6, 1. So this also cannot be called a partition because 1, 2 is here, 3, 4 is here. Then in this subset 2, 5, 6, 1 is again repeated. So again this cannot be called a subset. So these two conditions just have to be taken care of while partitioning a set, that no element must be repeated in a subset and all the elements must be there in one of the subset, in at most one of the subsets. So then you can call them partitions. So this is the condition for partitions. So this was all about the closure property in partitions in today's lecture. In the next video or in the next lecture, we will start with functions. So thank you for now.